Hello everyone, so welcome to our webinar this week. Coming today is Scott Lindstrom. Finally, he's made it to Curtin University. Previously, he's worked in Hong Kong Polytechnic as a postdoc, and also he obtained his PhD in the University of Newcastle under the supervisions of three different people: John Bowen, Barry Sims, and three Hanks, Bounce, and two other. Sorry, I don't know.
A lot of people.
Yeah, a lot of people. And this is great to have him here presenting to us about the top and primal dual computable approach to improve scaling algorithm based on minimizing spheres called I'm sorry.
You made it as long as possible.
I'm sorry, yeah, but now the stage is yours. Sorry for a very unprofessional introduction.
That's a great introduction. So thank you for the introduction, and thank you to everybody who's here. And here we go. I'll try to see who all is here. Thank you all for coming. Oh, Bruno made it. It is a pleasure to be back here in Australia, and finally, I've put here in brackets, I'm at Curtin University finally, and I was sharing a little bit of the story just now of the long journey to get home and be an Australian researcher again. And I did want to begin the sort of official recorded part of the talk by thanking, in particular, TK Pong, who found funds to keep me in Hong Kong until I was able to get into Australia, and also to thank Ryan Loxton and all of the staff in sort of the global office here at Curtin for all of the work that they did, which I know there was a lot of work that they did with the lawyers doing as much as they could to try to support the effort to bring us home. So very, very grateful to Curtin and also to TK and Polly Yu for all the support over the last year that has brought me to the point where I can finally put this Curtin University logo on my slides and work for Curtin doing optimization, which is what this talk is about. So let's do some optimization stuff. Okay, so we're interested in this pretty standard optimization problem, which is minimizing the sum of two functions, f and g. And these functions are coupled together through some kind of a linear equality. And for the sake of simplicity, you could just think of this linear operator as being the identity, and think of just minimizing a sum of two functions over some Euclidean space. And many problems can be coded up with this kind of a format, right? You could think about just the general constrained optimization problem, representing it this way by letting the objective that you want to solve be represented by one function, and maybe wrapping your constraints up into another function. And one way that you could think about doing that would be to define a function that is 0 whenever your constraints are satisfied and infinity otherwise. So for example, if one of your constraints was some sort of a linear constraint, for example, we want the solutions to live on this line, we could define a function that's 0 on this line and infinity outside this line, which we'd call an indicator function. And we'd minimize that function by projecting onto this line. And if I had a different constraint that my solutions needed to lie in this circle, I could do something similar with this circle, define a function that's 0 in the circle and infinity outside of it. And then iteratively minimizing these functions becomes basically projecting onto one set, projecting onto the other set. So I'm making one function 0 and the other function 0 until I find my way in here to this feasible point. And this method is called alternating projections method. And I'm sure most of you have seen this or something like this before. It's an example of what's called a splitting method, because it takes the two functions involved and it allows us to consider each of the two functions, first the one and then the other. So we're considering them separately. And so these splitting methods can be used to decouple constraints that are hard to satisfy simultaneously, or decouple minimization steps, or decouple constraints and minimization steps, or combinations thereof. And what I want to emphasize here from the get-go is, while I'm going to show a lot of examples that live in the plane, a lot of R2 examples, and in particular, I'm going to start by showing a lot of what we call feasibility examples, where I'm just looking for a point where two sets intersect. really I am interested in this much more general problem of minimizing a sum of functions. And those functions need not even necessarily be convex. So we'll spend the next little while hanging out in this graphical, dynamical interface of this program called Cinderella. And we'll see a lot of these examples in R2 of feasibility problems, but we are interested really in more general problems. And so here's the alternating projections method that I just showed on the previous slide. And as I drag this point around, you can kind of convince yourself that this is stable globally, right? Anywhere over here on the right that I begin from, I will eventually converge to that point where this circle intersects this line, which is the solution to this problem. Or if I were to start on the left, sort of a symmetrical thing happens. If I start here in the center on what we call the axis of symmetry, then I have an algorithm that's still describable, but we'd say it's chaotic in the dynamical systems sense that this central axis lies on the boundary between two different regions of stability for two different eventual destination points, right? And there's more than one way of defining an algorithm like this, a splitting algorithm that considers things separately. So here's another one called the Douglas-Ratchford method. And the basic idea of the Douglas-Ratchford method is that after I project, so I have a starting point here that I've labeled X. After I project onto this first set, the sphere, I'll go twice as far, which we'll call a reflection. That brings me to this point right here. And then I'll play the same game again. I project onto this line, but I'm going to go twice as far, which again, we'd call a reflection. So I've started here, reflected across the circle, and then reflected across the line. And so I've built this triangle where two of the vertices are sub-steps. They're these reflection points. And then to complete the iterate update, I simply take where I ended up after that second reflection and I average with my start point. And this, we would say, is my first update of this governing Douglas-Ratchford sequence. So if I play this game again, I reflect across the circle and I reflect across the line and I average. That brings me to this point, which would then be my next update. And I can continue playing this game. And as I iterate, my sequence of iterates will make their way in here towards this point where the circle and the line meet, which is, of course, the solution. And I can drag this starting point around and you can sort of convince yourself that there's probably global stability here for this sort of algorithm as well for this particular kind of problem, just as long as I don't start right on that central axis in that chaotic set. And this was first studied, this particular example, a circle and a line, by John Borwein and Braley Sims. And they were interested in it because it's its geometry resembles something that you encounter for something called a phase retrieval problem that Matt Tam actually gave a seminar about sort of recently. And but they didn't have a way of proving that this converged, but they decided to use a sort of visualization technique. So they used Cinderella, this applet that I'm using, and they plotted this plane, this sort of rainbow colored grid of points. And then they ran the algorithm to various numbers of iterates. So there's 1 time running it and 2 times running it, 3, 4, and watched the evolution of this dynamical system over time, where the time is given in these discrete steps. So we're seeing where points go. And maybe you're hearing my computer fan spool up there as it's doing a lot of computation. But you can sort of convince yourself that, that you can see that these points, this entire grid is slowly kind of twisting and swirling as these points make their way in here towards this feasible point. And this convergence was eventually proven. And I'll show you how in just a second, but before we get there, I'll show you another kind of nice functionality that these kinds of dynamical tools like Cinderella have. So if I take this circle and I stretch it out into an ellipse, which I might do if I was trying to learn about sort of the sensitivity of these algorithms to perturbations of the constraint sets, and which we did in this sort of follow-up article here with John Borwein, Braley Sims, Matt Scarrett, and Andrew Schneider. I can use this dynamical software to observe things that I would probably never come up with by hand. So here you can see there's a pair of, there's 2 subsequences going to 2 different limit points. Or if I drag this over here, you get 3 subsequences going to 3 different limit points. if I were to drag this to, let's see if I can make anything more interesting happening. There's 5 with 5 different limit points, and 7 with 7 different limit points. So you can see the kind of the complexity of this behavior. And if you, when you get these emails from the Mukau group about the Mukau events and about this seminar, you get this, there's a picture that has sort of a brown kind of plane, and in that brown plane there are these different kinds of swirling patterns and shapes. That picture is actually based on a study of this dynamical system for one of these ellipses and a line like in this configuration. So it's showing you sort of global behavior of that dynamical system in terms of its basins. So it just sort of illustrates a nice way of using this kind of a tool. And as I mentioned, for a circle and line at least, this was eventually proven by this fellow here, Joel Benoit, in his first paper that I'm highlighting for you. And he proved this convergence for a circle and a line, or a sphere and a line in Rn more generally, by building this object that I'm going to show you here called a Lyapunov function. And if you're not familiar, you can think of this function as simply being a function that describes for you the energy in this dynamical system. So it has bigger values out here where there's more movement in the system, and it's taking smaller values in here where there's less movement, and it will actually have a 0 for this function right here where these two sets intersect, because that's a fixed point, so there's no energy for the system right there. And this idea has been generalized. It's been done for more general sorts of graphs of functions by Min Dao and Matt Tam in this article here. And also it's been used, a similar construction has been built by Ohad Galati and Bjorn Ruffer based on unions of lines, which is another non-convex problem. These are all non-convex problems, actually. And what all of these constructions had in common is that they exploited a certain geometric feature that this Douglas-Ratchford algorithm has when these iterates are spiraling. And they use this particular feature here, which is that this Lyapunov function's level set curves, they're at a tangent to these difference vectors that connect subsequent iterates, right? You can see that here for this iterate, and you can see that here for this iterate as well. And more formally, you can actually write out that the gradients of these Lyapunov functions, or the subgradients, are orthogonal with these difference vectors. And that's sort of an interesting thing. And that's, there's actually quite a lot you can do with that kind of a property from a theoretical standpoint. Of course, checking for this property is a challenge, because in order to check for this property, you need to first know the Lyapunov function, and knowing the Lyapunov function is really equivalent to having solved the problem, right? Because if you know the Lyapunov function, you know it's 0 right here, which means you know that is a fixed point. So you know that's a solution. So for a real world application, verifying this kind of a condition is going to be extremely hard. But there are other things that you can observe that can point you to the possibility that your algorithm is spiraling in the way that this Douglas-Ratchford algorithm is. And I'll show you one of those ways, one of those things that we can look for. So from a theoretical standpoint, I'm interested in this orthogonality condition that relates the gradients of these Lyapunov functions to these difference vectors. But from a practical standpoint, I'm really looking for the feature that I'm going to show you here on this next slide, which is something that you can observe in your convergence analysis. I'm going to do that. Okay. All right. So what I'm going to plot you here are the horizontal changes from iterate to iterate. And these horizontal changes, so the horizontal distance from this iterate to this iterate, is the difference between the projection of this iterate onto this line and the projection of this iterate onto this line. So these are really differences of what we could call a shadow sequence of projections of these iterates onto this line. And this is a concept that has an analog for more general optimization problems, because a projection operator is a more specific example of something called a proximity operator. So if I'm looking at the differences in this shadow sequence, I'll notice that as I reach the side of this spiral, there's very little change. There's very little horizontal change from one iterate to the next, because I'm mostly going up and down, right? So I'll see there's a little dip in the change from iterate to iterate. But when I come over the top of this spiral, there's more change. So you can see I kind of go up a little bit in this convergence plot. But when I reach the side, again, there's less change. It's mostly vertical. And when I come around the bottom again, there is more change because it's more horizontal. Then at the side, mostly vertical. So there's a dip. Then as I come around the top, it's mostly horizontal. So there's a peak and a valley, a peak and a valley. And I get this sort of tombstone effect. And what's really nice about this is even though I'm not formally defining this tombstone effect in some rigorous mathematical sense, this is something that you can very easily check for in computation. You can very often see a pattern like this jump right out of the performance monitor. And when this happens, what I'm thinking is this lower dimensional sort of tombstone effect is representing for me a lifted dimensional sort of spiraling effect that's happening. So that's what we can check for. And the theory then is going to come from this idea of these Lyapunov functions having this orthogonality condition on them. And the reason that I'm interested in exploiting this theory is if I have an algorithm that's spiraling, I would like to make it go faster by using that geometry, exploiting that geometry in some sense, and exploiting what I might think about that Lyapunov function in order to make it go faster. So let me show you one sort of example of this. And this is something called the circumcentering-reflection method. And in order to sort of understand how this works, you'll need to understand what a circumcenter is. And a circumcenter is just the point that is the circumcenter of 3 points, A, B, and C, is the point that is lying on the circle that contains A, B, and C. So it's equidistant from all of them, and it lives on their affine hull. And in this situation where you have these 3 points are not collinear, it's a sort of well-defined thing, but you do need to be careful in computation because if you do happen to have 3 points that are collinear, of course, that circumcenter will live at infinity, which would not be great for computing. So you do need to make sure you have some kind of a tolerance, some kind of a check built in to make sure that that doesn't happen, or that you continue to use regular updates if that does happen. And I won't talk too much more about that. But let me show you how this is used in computation. Oh, before I do that, let me point out another characterization of this. This purple point lives on the intersections of these 3 perpendicular bisectors for the 3 sides of the triangle generated by these points A, B, and C. That's kind of a key way of thinking about this. And this has been used in the construction of this algorithm called the circumcentering-reflection method. And essentially, the way that this algorithm works is we have a starting point. We build that Douglas-Ratchford construction triangle as we did before. So we project onto the first set, reflect, project, reflect, and then we have a triangle where 2 of these vertices are built out of these reflection substeps. And then we take the circumcenter of the 3 vertices of this triangle. So that includes these 2 reflection substeps and this starting point. And that would bring us to right here, because the perpendicular bisectors of the 3 sides of these triangles, one of them is just this line itself, right? That's the perpendicular bisector of this side. The perpendicular bisector of this side here is a tangent to the circle. And so this maybe reminds you a little bit of Newton-Raphson method, right? This is sort of how we introduce our students to Newton-Raphson method. We say you start in the axis, you go up to the curve, which is the graph of your function, and then you follow the tangent back to the axis. And actually, you can use this characterization of this particular method to show quadratic convergence for certain kinds of plane curve problems, which I've done here in this article with Neil Dyson and Jeff Hogan. But what I think is much more fun than that is that you can actually use a sort of classical result called the generalized angle bisector theorem to show that this will find the root of the square root function and do so at a rate that's superlinear. And of course, you wouldn't actually want to use this sort of a thing to find roots of curves because the computation of the projection itself is just as hard as finding the root of a curve. But this study of the sort of the complexity and speed of these governing sequences is interesting because it tells us features that these algorithms might have more generally, right? So here I'll show you the convergence of this just because it's fun, right? I project onto this curve and then I follow the tangent, which brings me to the line, and I'll connect my subsequent iterates with red curves now, just so it's visible because they're all going to live in this line. So that's my first update. That over there is my second update. And that there is my third update. And if I keep playing the game, I'll converge finitely on the 7th or 8th update right there, which is just kind of fun. I think it's really fun to use some sort of a classical result like the generalized angled bisector theorem to prove something with plane curves, although referees don't necessarily agree with me about that. But anyway, as I mentioned, we're interested in this more general optimization problem. We're not just interested in finding points in the intersections of plane curves. And in particular, I want to build something that can make these algorithms that can run faster than Douglas-Ratchford or alternating projections for some kind of a primal dual implementation of an algorithm. And what I mean by that is that if you're familiar with this, awesome. If you're not familiar with this, you might maybe are familiar with the sort of Renaissance geometry notion of duality, where you can take, for example, a polygon like a triangle and apply some kind of an operation to that triangle, and it then turns into a different triangle. And if you apply the same operation to that second triangle, it turns back into the first one. So we have a notion like this for convex optimization, where we can take the graphs of these convex functions and sort of the area above them, and we treat them like they're a polygon. So here is the absolute value function, and it has sides and vertices, and there's a sort of geometry rule that we follow, and it transforms into a different triangle. And this is the epigraph for a function that's 0 on the interval from -1 to 1. And if I then apply the same set of geometry rules to this function over here on the right, it turns back into this function on the left. And from these convex ideas, we get this idea of duality of algorithms, right? Where if there's an algorithm that's solving a problem related to this, this function here, it has a sort of twin that lives out there in the ether solving algorithms that are related to this sort of partner function. And this idea can extend even when I'm not working on a convex problem necessarily. And I'm going to exploit it here for and show you an example of a primal dual framework for computing. So the problem that I'm showing you on this slide is something called the basis pursuit problem. And the goal is to find a sparse solution to a linear system. That linear system is represented by this blue line right here. And the algorithm I'm using to solve it is something called alternating direction method of multipliers. And the optimization problem is to minimize this one norm, whose level curves I've shown here in gray, subject to the condition the solution lives in this blue line. So it's a constrained optimization problem, but we're not just finding a point in the intersection of sets, we're really minimizing a function now. And you can see here this algorithm, ADMM, is working just fine to solve this. And I want to draw your attention to these purple points, and I won't explain every aspect of how this construction works, but these purple points are a part of this ADMM algorithm. And specifically, these are shadows of its dual partner, the Douglas-Ratchford method. And I'm going to plot for you the change from one iterate to the next. And as I do that, you can see there's a peak and a valley and a peak and a valley at regular intervals. And what that says to me is that maybe if I reconstruct this dual partner, this Douglas-Ratchford algorithm, I will see that it is spiraling in some sense. And I can use information about these algorithms that's found in this very wonderful reference by Daniel Gabe, and also this wonderful paper by Extant and Yao, to reconstruct, basically just directly from the geometry, this dual partner algorithm. And you might wonder, what problem now is this dual algorithm solving? And it doesn't really matter for our purposes, right? It's constructible from the main iterates that we can compute with, these ADMM generated iterates. We can backwards compute this. And actually, this is the Douglas-Ratchford method for solving this sort of related optimization problem. And it is spiraling. So what I would like to do is design an algorithm that allows me to jump to the center of this spiral and then use that to update these purple variables and then sort of backwards update these orange and green variables involved in the primal algorithm in order to speed that primal algorithm up. So I'm computing with the primal algorithm. I'm then using geometry to speed up its partner, and then I'm sort of passing an update back to the primal algorithm. That's the goal. And maybe the naive way to approach this is to just attempt to use circumcentering reflection method for this more general optimization problem. And it doesn't work very well, or it doesn't work at all, I should say. And let me explain why. So I've taken here a Douglas-Ratchford iterate, Y4, and I've computed the subproblems. So the subproblems are this reflected projection operator here, and this, what we call a reflected proximity operator here, which is a more general kind of concept. And then I've centered them, or I've taken the circumcenter of these 3 points. And remember that circumcenter lives on the intersections of the perpendicular bisectors of the sides of this triangle. And so that means that it is going to live in this vertical line right here that I'm highlighting for you, because this projection right here is a projection onto this pink unit ball in the max norm. And as a result of that, this perpendicular bisector is going to contain some face of this unit ball in the max norm. And I have no reason to believe that this circumcenter update is going to lie anywhere close to the center of my spiral, which is way over here. In fact, if I attempt to compute with this, it's not going to be able to improve my performance. Right? So I would not expect anything good to come from simply adapting this circumcentering reflection method for this more general framework. And the problem that I want to highlight is that it's caused by these reflection operators, right? I'm using these to build a triangle, and I'm circumcentering the points, the vertices of that triangle. But if I can get rid of this dependence on these subproblems, then maybe, and find something that just uses these main iterates, these spiraling iterates, to find the center of that spiral, then I might be able to actually come up with something that can help me solve this problem faster. And for inspiration, what I did was I took this circumcentering reflection method and I plotted it, and over the top of it, I plotted the level curves for this Lyapunov function for the Douglas-Ratchford method. And as I sort of drag this around, maybe you can notice the pattern that I noticed when I looked at this. Maybe you can see it. The pattern that stands out to me is that this circumcentering reflection method update, this purple point here, really looks like a step of gradient descent applied to this Lyapunov function. In fact, from 3 points, from this point right here, from this point right here, and from this point down here. And this is something that you can prove, that it has this characterization, that this update lies on the intersection of these gradient descent trajectories. And the proof is very complicated, but it's very easy to see. And that's something that's really nice here. And once you can see a pattern like this, you can use it as motivation for designing a new algorithm. So when I saw this, what I thought was, I want to build something that retains this property, but doesn't use these reflection substeps at all. And so here's the most natural one to come up with, and there are others, and I'll describe some of these other ones as well and how we can think about these other ones. But what I've done here is I have 3 steps of the Douglas-Ratchford algorithm. So there's no reflections here. I'm not even plotting reflections. I'm just showing you the main governing sequence iterates for this algorithm. And what I've done here is I've taken this first iterate, the starting one, and reflected it across the first update to get this little green point over here. And then I've constructed this salmon colored point that I've called pi out here by taking my starting iterate, adding onto it 2 copies of this difference vector, and then adding onto it 2 copies of this first difference vector projected onto this second difference vector. And as I drag this around, you can maybe kind of convince yourself that this algorithm will have this property, that it looks like a step of gradient descent applied to this Lyapunov function from 2 points of perspective, from this update here and from this update here. But it will also have another really interesting property, which is that it's going to live in the affine hull of these three governing sequence Douglas-Ratchford iterates, which is a sort of an interesting thing, because right away it means that if the Douglas-Ratchford method is taking a subspace of reduced dimension into itself, this new method I've introduced here on the right is going to do the same thing. And that actually makes it very easy to prove this result, which is that if I use this method for the feasibility problem of two lines in Rn, it will solve this problem in one single step every single time, because the Lyapunov function in question, and this is proven in Mindau and Matt Tam's paper that I referenced earlier, this Lyapunov function is just a spherical function. It's perfectly symmetric, and all of its gradient descent trajectories lie in the fixed point set. So it doesn't matter how I organize these lines, doesn't matter where my starting point is, I always solve it in one iterate, which is fun, first of all, and really a free result, but also suggests a deeper intuition behind what this algorithm is doing. Namely, this algorithm is returning me the minimizer of a spherical surrogate for this Lyapunov function, right? And this spherical surrogate is sort of gradient matched on this reduced dimensional subspace at 2 points, this one here and this one here. And this is a powerful thing. And it's also, I want to draw your attention to the fact that in this case on the right, there's no reflection operators used. And the only assumption that you need to have to prove that this algorithm will have this spherical surrogate minimization property is the assumption that this Lyapunov function has that property of the orthogonality of these gradients with these different vectors. As soon as you assume that, you automatically have this spherical surrogate minimization criterion being satisfied, with no other structure really at all. For this algorithm on the left, in order to prove this sort of a relationship, I had to assume a whole lot of structure. I had to assume basically all the structure in Mindau and Matt Tam's paper. I had to assume this is a feasibility problem. I had to assume these are graphs of functions, which is restrictive, right? It gets rid of this more general optimization framework. It's excellent as far as building this kind of beautiful theoretical understanding. But if I assume all of that structure, I'm immediately losing out on something potentially like a basis pursuit problem. And the second thing I want to draw your attention to about this is that because I don't build this out of these reflection substeps, this algorithm on the right, if you handed me a black box that was spitting out algorithms or iterates that spiraled, if I was looking at this performance monitor and I could see this sort of tombstoning effect, I could apply this algorithm on the right to that without knowing how that algorithm works. Whereas on the left, I would need to know these sort of reflection substeps. So there's a great deal of utility that this algorithm on the right has that this algorithm on the left doesn't have. And you could also, as far as thinking about minimizing these surrogates, there's many different directions you could go. This, I think, is the most natural one because it's a spherical surrogate built on basically a two-dimensional affine subspace. But you could do something more interesting and exotic. You could, for example, build an elliptical surrogate where you sort of take more iterates and build more data into approximating this Lyapunov function and returning minimizers of it. So here's an example of an elliptical sort of surrogate. Or you could do what I think is maybe a more natural generalization, which is that you could build a higher dimensional spherical surrogate. Ellipses are tremendously unpleasant to work with for numerical reasons. But if you look at this image right here, think about what's happening here. You have a problem that lives on a two-dimensional affine subspace. And this problem can be solved. I defined it in terms of this circumcenter operator. But if you forget about this circumcenter operator entirely, think about what's going on here. You have two linear equations, right? You have one linear equation defined by this perpendicular condition, and you have one linear equation defined by this perpendicular condition. So you have two linear equations in two variables on R2. There's a unique solution. It's this purple point here. If I add another point to my construction, as long as these 4 points then used in my construction define a 3-dimensional affine subspace, I now have 3 linear equations in 3 variables, and they're defined on this, and this is a problem that's then well defined and it has a unique solution. I could build spherical surrogates that are higher dimensional surrogates, or I could even design an adaptive framework that attempts to use these lower dimensional surrogates, and if that's not returning me better solutions, just continues computing with regular updates and takes those regular updates and builds these higher dimensional surrogates and sees if any of those might give me a better solution. So there's all kinds of directions that you can potentially go in as far as building higher dimensional spherical surrogates, and it's all very solvable. And because I don't have any reliance on reflections, I would think that this simple algorithm might work for something like the basis pursuit problem. So let's actually see how well it does. So here I've taken a Douglas-Ratchford step and the next 2 Douglas-Ratchford steps. So I've taken these 3 points and I've built this new sort of Lyapunov function minimizing construction. So I've built I've defined this in terms of a triangle and a circumcenter, but again, remember, we don't have to do that. And let's compare this update, which is here in green, to what would happen if I had just computed regular updates. Well, this green update is certainly better than 1 regular update. It's better than 2, 3, 4, 5, 6, 7, 8, at least better than 8 regular updates. I'm not sure whether this actually solves it finitely or not. I'd have to do more kind of work to sort of tease that out. But you can see, at least for this basis pursuit problem in R2, it works quite nicely. And you might ask, does this work for a basis pursuit problem in higher dimensions as well? And there is this slideshow that goes along with this, and the numbers match the frames of the Cinderella slideshow. So I'm going to fast forward through the slideshow to the ending here. So here's an example of a 300-dimensional basis pursuit problem. And here's this new algorithm here in the purple and yellow. And here's the competitor of vanilla ADMM here in the red and blue. And I should mention here that I'm including in this construction a check of the objective function at each time that I compute this sort of Lyapunov function minimizing update, where I basically ask, does this update perform better than a regular old iterate does in terms of improving my objective? And if not, then I just compute with a regular iterate. And you can see this probably solved this maybe 7 or 8 times faster. And that seems to hold sort of more generally across the experimental data. And this method was faster 999 times out of 1,000. So there's, and of course, one time it was not faster, so that's kind of interesting, and there's certainly plenty that can be looked at here. And of course, the difficulty of proving anything here is that this method really is not built out of directly out of the problem structure, right? It's built out of the combination of the problem structure and the algorithm structure, right? Because these Lyapunov functions are built with data from the algorithm, in this case, the Douglas-Ratchford algorithm. And so in terms of actually proving some kind of a convergence result, it would be very, very difficult, and you'd need to know probably about these Lyapunov functions, which in some sense is almost equivalent to knowing the solution. So this is showing convergence results isn't necessarily the most natural direction to try to move in right away, unless you were to start with a whole lot of structure. But it's sort of an interesting idea, right? This notion of minimizing the Lyapunov function for the algorithm, rather than it's sort of minimizing algorithms on algorithms, so to speak. So just to sort of summarize what I think are some of the key contributions here, I think that this Lyapunov function characterization of CRM might be useful for people working on the circumcentering reflection method, CRM, which I'm less interested in, but for people who are interested in that, this is a characterization that now holds, including in non-convex cases for these kinds of spiraling situations. And then sort of more interestingly is this new class of methods, right, that really are problem agnostic and operator agnostic, in the sense that if my iterates are coming from ADMM or Douglas Ratchford or some primal dual sort of setup, or even if somebody just hands me a black box that's spitting out algorithm points that are spiraling, I could use this kind of a method and adapt it into that code structure without needing to know substeps and without really needing to know that much about the actual problem. In particular, if I have some kind of an objective function that I can check and make sure that I'm not, making things worse. And this isn't convexity reliant, right? Most of the examples that I've shown you, at least the plane curve ones, are non-convex. And we've also used this, Neil Dyson and Jeff Hogan and I have used this method for finding wavelets. And it seems to work very well. And that's even without an objective function check. So for both of these methods, there's this nice quadratic surrogacy characterization, right? Which can really be extended, right? In this first project, I've only used these sort of two-dimensional spherical surrogates, but you could look at something like higher dimensional spherical surrogates or an adaptive framework. And so if you're not interested in this topic really at all, hopefully some nice takeaways are that tools like Cinderella and GeoGebra can be really useful for visualizing the behavior, especially for things like dynamical systems. And another sort of takeaway lesson is that these excursions deep into the weeds, right? So highly structured problems, things like looking at circles and lines, spheres and lines, can yield really valuable insights about more general problems. And then sort of a last sort of point here is that looking for bridges between seemingly disparate areas of research can be really fruitful. So the main sort of motivation that provided motivation for the design of this new algorithm here on the right was just plotting the circumcentered-reflection method over the Lyapunov function here on the left. And that's really as easy as just sort of copying and pasting a few lines of code and looking and seeing if there's anything there that's worth observing. So that's most of what I had, and I'm happy to answer your questions. And thank you for attending my first talk as an Australian researcher again.
I'm stepping in. It looks like Hua, our chairperson, had to leave to some meeting. At least she's shown here, but I don't see her. Anyway, thank you very much, Scott, for your very picturesque presentation. So welcome back to being an Australian researcher.
Good to be back.
And we are glad to have you here. The topic is probably of interest for many people in the audience, and I expect a number of questions. So please, if anyone is willing to ask a question, just unmute yourself and go ahead.
Oh,
Curtin.
Me. Okay. Thank you for a great talk. Welcome back to Australia. Really positive news. Very much enjoyed the talk. Thank you. I just maybe it's more of a comment than a question, but so for systems theory in general and control, the concept of quadratic Lyapunov functions has a very dominant role. So basically functions that are of the form vector times a symmetric positive definite matrix times the same vector again. And in a way, the circle approximation fits this description or fits into that framework of quadratic functions, obviously. And it would also comprise more general geometric shapes like ellipses. And it also extends possibly nicely to higher dimensions in a way. But of course, the question is what specific quadratic would you choose and so on. And so so I guess now the question part, have you thought about quadratic functionals in general as your Lyapunov functions specifically?
Yeah, that's a good question. And actually, I'm glad you asked it because it's probably one of the only sort of future research questions I can answer because it's been a busy few months. for a lot of reasons. But yeah, this is one of the only things, follow-up things that I've had a chance to kind of take a look at, which is I took a look at using ellipse type constructions, right, with various numbers of points, thinking, okay, maybe in sort of higher dimensions, these basis pursuit problems, maybe I'll get a faster solution using an elliptical sort of thing. And the reason that I wanted to look at that is actually that if I were to zoom in on this convergence plot that I showed you here on this slide, if I were to zoom in on it, you would see that actually many of these centering updates are getting rejected. And so a small number of these Lyapunov function minimizing updates make a huge difference, right? Over the course of, I guess this maybe is 250 iterates. There'll maybe be, maybe be 5 or 6 that are really consequential. And for the most part, a lot of them aren't helpful, but those ones that are consequential are tremendously helpful, right? And so my thought was maybe if I just change the geometry, I'll end up with something that's helpful more often than a sort of perfectly spherical thing. But what I found is when I used this more general elliptical thing, and no matter how I sort of designed these ellipses, and no matter how many iterates I sort of built into the construction of them, they performed better than ADMM, but they always seem to perform worse than just using a straight up sphere, like not warped, not bent, which maybe has something to do with the basis pursuits, the geometry of that specific problem. And maybe there's other problems where something like an ellipse would work better. But I did think it was really interesting. I was kind of had high expectations that these ellipses, because they're more flexible, might do better. But the sphere always wins, at least in my so far basis pursuit category experiments.
But it may have to do with the type of problem you're looking at. I mean, it's just a wild guess, but there's always a line in your examples, it seems, and maybe the I don't know, if you depart from the line and something paradigm, maybe then they become useful. So
I'm very interested in, by the way, if anybody knows sets of problems that have this tombstoning feature. I just want to make like a bank of ideas for problems to try out these surrogates on. So I've only done basically basis pursuit so far, and then like feasibility problems. But I would love to have more, especially more like primal dual problems that have these kinds of patterns to test these surrogate minimization things out on. So if anybody knows any, definitely, I'm happy to start making a list.
More comments, questions, please. Bruno, please.
Hi, Bruno.
Hello. Thank you very much for the very nice talk. And actually, I have a question, not exactly about the contents of the talk, but your research process. So for example, the programming of Cinderella and creating all these scripts. So was it something that came first? So you first tried a bunch of things in Cinderella, and then this gave you some ideas of how to prove stuff, or was it something, for example, that you did in order to explain these ideas better to other people? I'm just curious about this.
It's a mix of the two. In terms of coming up with the new algorithm, I actually came up with this new algorithm accidentally in a different way first, by solving there's a symbolic problem that I solved, which is what would happen in order for two successive Douglas Ratchford iterates of the same sequence with their constructions to possess the same CRM update. And if you solve that problem, you actually get something that's related to this. But then when I actually began writing, when I went to sort of experiment and play around a little bit, I don't remember exactly when I did this, but I then put the Lyapunov function over CRM to sort of look and see if there was anything there that I could tie back to this. And that's when I sort of realized, oh, there's this gradient kind of relationship between these. And then that led me to start thinking about, oh, but I could actually describe this thing as a more, really as an example of this other thing. And that's really the more natural way to think about it. So when I actually wrote the paper, I didn't include in the paper the way that I first came up with this, because it just seemed like a really unnatural way of thinking about it. And I think maybe the more natural way of thinking about it is what I sort of discovered by playing around and experimenting. And I would say very often the process of playing around with Cinderella has led to the ideas, probably more often than the ideas have led back to Cinderella. So, yeah.
Thank you.
Next. Who's next to raise the hand and ask questions, make comments? Matt, please.
Yeah, thanks for your talk, Scott. I have a question about the circumcentering operation. So most of the time you're doing it with just 3 points, like with the triangle, right?
Mm-hmm.
But I know that Heinz, Bauschke, and co-authors have a paper where they look at a version of circumcentering where they allow like finitely many points, and they analyze that circumcentering operation. Could you imagine also doing something with more than 3 points? Because 3 points is kind of like makes sense for Douglas Ratchford, but yeah, have you thought about that, I guess?
I haven't. I really need to look at their construction and see sort of how it relates. I'd be interested in seeing how it relates to this idea of building a sort of a sphere, right, with points, or a spherical function with points that live with these sort of tangent things. And I wonder if there is some relationship there. So that's I think it's a good question.
Okay, thanks. I know that I have some results about like fixed point sets and stuff like that. Like you know, when you do the let's say generalized circumcentering operation, fixed point sets behave well, let's say. But yeah, also not an expert on that. But okay, thanks for your comment.
It's a good question. I think it's definitely worth looking into. I'm excited about this topic because there's just so many different questions that I now have. Where, you know, usually when I finish a paper, I have lots of follow-up questions, but I find them all boring. And this time I like all of them.
Okay. I don't see any more hands raised. Last chance to ask a question. Okay. Scott, I have a feeling that some people in the audience who don't know the history of your travels might find this last slide a bit misleading. Just for the audience, Scott is now in the west of Australia, Western Australia, in Perth at Curtin University, and picture shows as if he arrived in Brisbane, which might be true in terms of aviation, but finally he landed in Perth. Just a correction.
Yeah, a few days before we were set to fly, I think 4 days before we were set to fly, the Premier of Western Australia decided that there were too many people coming to Western Australia, and so decided we need fewer people coming to Western Australia. So the airline informed us that our seats had been changed. And upon very careful reading of that email, we discovered that our flight had actually been changed and we were being sent to Brisbane. Apparently a fully vaccinated person and an unvaccinated person, both from Hong Kong with fewer COVID cases than Australia, were the people that they moved to Brisbane to reduce the risk. But we were just happy to get in the door. And laugh at the sort of way decisions are made, but just happy to get into the country. So this is the coming home.
Sure. So just a small excursus in geography. Anyway, thank you very much, Scott, for your nice, beautiful presentation. Thank you for your patriotic move to Australia. And please keep coming to our webinar with new presentations, new pictures. Now probably everybody in the audience loves Cinderella, and we are looking forward to seeing new beautiful illustrations. Okay, if no more questions, then thank you, and see you, all of you, next week. Finished.
Thank you.
Thank you, Scott. Very nice talk.
Thank you all.
Bye-bye, guys.